Lunch, let's get seated. Okay, the morning, what did you guys think about the morning sessions? Okay, all right, good. Yeah, I thought it was awesome. So we now are starting our afternoon session, so we'll have Professor Derek Hoiem come to stage, and he's currently a professor at University of Illinois and CTO of Reconstruct, and he'll be talking about 3D computer vision and 3D reconstruction. So thank you.
Thank you. All right, good afternoon. I hope you all enjoyed your lunch. So I'm really happy to be here. It's really fun to give a talk to people that are not all computer vision people, and to also hear about all the things that other people in other fields are doing. So the problem I'm going to be talking about is taking a photo or set of photos and creating a 3D model of the scene from those photos. So it's basically a problem of transporting from a 2D representation, the photo, to a 3D representation of the scene. And it's really a tale of two technologies. There's two completely different branches of ways that this problem has been solved. So one is the more old school, traditional geometric algebraic approach, where if you have multiple images, then you can treat the problem as one of correspondence and triangulation. Basically, the idea is that if you have two different photos of the same area of the same scene, and you can find corresponding points in those two photos that view the same scene point, then you can triangulate through those points in the image to solve for the 3D depth of that matching point. And then if you do that for a lot of points, then you can solve for the 3D geometry of a lot of the points in the scene. So this approach takes multiple images. You solve for the poses of the camera. You solve for some of the 3D points in the scene. And then you often fit the structure of the scene to those 3D points that you've reconstructed. So you might fit CAD models or align other representations of the scene. You might fit surfaces or geometric representations like blocks. So this is the approach that I really obsess about as CTO of Reconstruct. It's a well understood process in many ways. We can create reliable processes that we can communicate to drone operators or other people taking pictures so that they can take pictures in a way that will reliably produce good models, good detailed models that are useful for many applications. The other branch almost goes backwards. So in the other branch, you just have a single image. You can't triangulate because there's only one vertex of the triangle. So you don't have any 3D information that's explicit in that one image. You just have to somehow magically hallucinate a 3D representation from a 2D representation. So the approach is to go the other direction. You start by trying to recognize the structure of the scene from the image. So for example, here, which parts of the image are ground, vertical, or sky? And then you fit the geometry to that structure. And usually it's a very simple model that you're fitting. You're trying to pull something from nothing, 3D from 2D, and so you have to keep it simple and have just a very abstract representation that you're trying to infer from the image. And this is what I obsess about as a professor at University of Illinois. It's much more of a research problem, and it's a problem of recognition. And these two branches are completely different technologies. Somebody could be, the only thing that they have in common is the basic camera geometry. Otherwise, somebody can be an expert in multi-view geometry, the left branch, and know nothing about how to extract 3D scene information from a single image. Or somebody can be really good at extracting 3D scene information from a single image and have no idea how to do multi-view geometry. So what I want to talk about is what is the state of the art in each of these two branches. So what can we do now? And I'll show you some example applications. What is the bleeding edge? So I'll show you in each case one example of some of the most recent research that's not really ready for prime time yet, but it gives you an idea of what might be ready for prime time soon. And then I think what's really exciting is that there's the potential to unify these two technologies, these two different branches, to create methods that will be much more powerful than either of them. And so I want to talk a little bit about that. So first, let's talk about how we create a 3D model from multiple images. This can be extremely technical. I could do 2 or 3 lectures on it, and it would still not cover enough detail to really understand it fully. So I want to just kind of talk about it at a little bit of a higher level, enough to understand the basic processes and to understand what the weaknesses and strengths of the existing algorithms are. So there's basically 3 steps. The first step is that you have to solve for the positions of the cameras that took the images. So in this picture here, all of these little triangles are the 3D, they're representing the 3D locations of the cameras when they took a set of photos. In this case, the photos were taken by a drone, a mix of drone images, drone video, and a camera that was mounted on a crane. So this process of solving for the camera pose involves trying to find matches across the images, meaning that you try to find pixels in 2 different images that correspond to the same scene point. And that's something that became that we could do much more successfully starting around 2000, when good features were engineered for matching across images from very different perspectives. Then, if you can find enough matching points, then you can solve for constraints that give you the relative poses of 2 cameras and the 3D positions of those matched points. And then there's a variety of different algorithms for solving for all the poses. You can either start with a solution from 2 cameras and gradually add more and more cameras, or you can have lots of 2-camera solutions and then solve for a globally consistent solution. There's also, other variants like SLAM, where you have a video, but basically all of them are just trying to solve for what are the positions of all these cameras that took the pictures. The second step is where current technology can sometimes break down because it makes some assumptions that I'll get into in a minute. But basically, the idea is that you propose what 3D scene points might be there, so where a surface might be. Maybe there's one against the wall, maybe it's a little bit in front of the wall. And then you verify those scene points by matching, and I'll talk about that in a little bit more detail. And then finally, once you've got a point cloud, a set of the 3D points that you think are in the scene, then you often create a simpler representation by fitting a surface to those points. So a key step in this multi-view reconstruction process that I want to focus on is the step of verifying which 3D points are actually in the scene. So in this illustration, we've got a set of cameras, and this was created by Furukawa and Hernandez, by the way, in their multi-view stereo tutorial. There's a set of photos that are viewing the same 3D object, that statue. And the basic assumption of multi-view stereo, which is the process of solving for 3D points given multiple images, is that if you have given some point on that statue, if you look at it from different directions, it will look the same. So and that's true for many objects. If you move around these chairs, or you were to move around me and look at my shirt, and you fix like a point on my shirt, then no matter what direction you view my shirt from, the color of the shirt is going to stay the same. So that's true for what's called Lambertian materials, or materials that kind of scatter their light in all different directions. It's not true for reflective surfaces. So if you're trying to reconstruct points on windows or mirrors or glossy countertops, then that can create a lot of problems for multi-view reconstruction. The other assumption is that you've got some texture, because if you don't have any texture, then there's nothing to match. So basically, if you're verifying the match based on the patches across the images looking consistent, given that hypothesis of the depth, then basically, if you have no texture, then it's going to be consistent no matter what. So you have no information with which to estimate the depth. So given this process, we can take a set of 3D of pictures. We don't need to know GPS information or anything else. Purely based on analyzing the features within those images, we can create 3D models like this one. So this is showing the pose of the cameras, a point cloud, the 3D points of the scene that were reconstructed, and then you have all the images are localized with respect to that scene. So in some applications, it's useful to be able to dive into those images, see details, take measurements, and so on. So this process can give you very detailed, rich 3D representations of the scene, and it can be applied to tiny little objects, or it can be applied to huge multi-acre scenes. So I'll mention just a couple of applications, and these are things that we do as part of Reconstruct. So one of the applications is to try to simplify inspection in hard-to-access areas. So for example, if you want to inspect a big cooling tower, they can be 950 feet tall. You can't just, first of all, to take the photos, you can't just stand on the ground and take a bunch of photos. In the past, you might have had to fly an airplane to take some photos. Now you can fly a drone. But even if you fly a drone, let's say you go out, fly the drone, take a few hundred photos, then you've got this big folder of images. And the structure looks the same everywhere. So you then have a problem of like, where did these images come from? Even if you find like exposed rebar and cracks and stuff like that, you have no idea where it came from on the structure. So you have a really painstaking process of then remapping the images to some kind of drawing or representation of the structure so that when you find problems, you can go back and make repairs. Now, the advantage of this approach, if you can create the 3D model from those images, you have a nice model that you can use to simplify your inspection. And then you can also go look at the images in their original detail, registered to that model, make measurements, add annotations, and then export a report that tells you the 3D positions of all of these defects on the structure that you can then take to the owner and show them like what maintenance needs to be done, and then give it to your guys in the field so that they invest time in the right places to climb up and fix different problems on the structure. And this is a really big problem in much of our infrastructure: bridges, cooling towers, cell towers. Much of our infrastructure needs to be inspected between every 6 months to every 2 years, and it's really a pain. So another big application is in construction. So here, the idea is that we can create a 3D timeline that's visual and actionable. So we can combine this reality capture data, the 3D representation of the scene, with the building plans, the schedule of when things are going to be constructed, and a 3D model called a building information model that shows where all the elements are going to be constructed. By combining these different types of data, we can create a single interface where construction teams can see what's been built and how it corresponds to the plan. And that's a really crucial thing for construction because it's often hard to get timely access to progress. And even in little delays that can happen when you don't know that there was a problem on site yesterday can add up into months of delay and millions of dollars of cost overruns. So by combining these virtual models, the plans, with the as-built models, which I guess are still virtual but created from real images, we can create this kind of augmented reality. And it's a 4D augmented reality because we can do the reality capture, creating 3D models from the images over time, and then correlate that with the schedule and the building information model. So we've got a 4D plan and a 4D model of what's actually been built. So we can do things like color code to show who's doing what work on what location, show whether different parts of the project are on schedule or delayed, and then even apply machine learning algorithms to analyze constraints in the schedule, past productivity, in order to predict where delays are likely to happen in the future, so that construction teams can coordinate to head off those delays instead of reacting to them after they happen. So overall, this helps construction teams analyze, plan, coordinate, and stay on schedule. So the point is that being able to create these detailed geometric models from multiple images can really lead to some very impactful applications. There's many others as well in entertainment and so on, but these are some of the ones that I'm most personally involved with. So multi-view reconstruction is great, but it also has its problems. So one is just, it can be a pain to collect the number of images that you need with good coverage and good overlap. You often need to take the photos in a very systematic way. Intuitively, you might think that if I want to reconstruct the environment of this room, then I should make sure that I have at least one photo of every section of the room. In fact, you should have at least 5 photos of every section of the room. you need a lot of overlap and redundancy so that you can match points across the images and register them to each other and accurately estimate the depth of the scene points. And so that capture process of taking enough photos with enough regularity that you have the overlap and coverage you need it can be quite painful. And in many situations, like if you're doing this in indoor scenes, it can be difficult to communicate the methods of capture to photographers or even for experts to do it well. The second problem is this assumption of textured non-reflective surfaces. So here's an example of a steel structure where it's a bright day, so the steel is reflecting the sun or clouds or whatever that are in the sky, and that causes failures because basically now two images that are viewing the same point in the 3D scene are showing different intensities because one is reflecting the sun and one is not reflecting the sun. And then the third problem is just that this is a pure geometric representation. There's no semantics. There's no understanding of the structure of the scene. It's just geometry. And so that limits what you can do with it. Without understanding what are the objects and having a broader understanding, there's only so many things you can do. So the bleeding edge is really the application of deep networks to this multi-view stereo. And where they come in is in that feature matching. So typically in multi-view stereo algorithms, when you're trying to say whether basically when you're trying to say whether a depth hypothesis is correct, you're checking whether two patches match. So you might look at 2 3x3 patches in each of the images. And if they have a high enough correlation, then you'll say that depth hypothesis was correct. And that matching function is very simple. It could just be comparing the sum of squared differences or normalized cross correlation, some simple engineered function. Deep networks are able to learn features that can lead to more robust matching. So I won't go through the whole structure of the network. It's not that important. But basically, you're just learning a better matching function, and that better matching function leads to a better ability to say whether or not a hypothesized depth point is really there or not. And especially that can be more robust to smooth surfaces, textureless surfaces, and reflective surfaces, which are the problems for multi-view stereo. So here's an example, and these are not my works. One is the recent deep network approach is by Huang et al. From UCLA. And then CoalMap is an older slightly older multi-view stereo method that's more traditional. So you can see here this image of the hallway. There's glossy surfaces. There's a lot of smooth walls. So this is a challenging scene for traditional approaches. In CoalMap, the traditional approach has many areas shown in black there where it wasn't able to reconstruct the points. And then the deep network approach was able to reconstruct a more complete model. Now, these deep network approaches still have not yet achieved the overall accuracy and precision of the more traditional multi-view stereo methods, but I think they'll be there in just about a year. Okay, so that's all from multiple images, but I think conceptually this should be somewhat dissatisfying in some ways because we all have the experience that we look at images and we still feel like we understand the 3D structure of those images. It doesn't feel like we need to see it from we need to see the scene from many different angles in order to understand the geometry. So if you're looking at this image, for example, you can tell that which of the bicycles are closer to you than others. You can see that the trees are in the lawn in the back, that the horse is before the cart, and so on. So there's a lot about the 3D structure of the scene that we understand, and in fact, we feel like we have a pretty good grasp on the action space around us as well as further points in the scene. So there must be some way to get something about 3D from just a single view. So I actually started thinking about this problem when I was a graduate student around 14 years ago, and this was the image that first inspired me. So when I looked at this, I was thinking, okay, so there's dirt, there's like two sections of dirt here. There's a bunch of dirt on the ground, and then there's a bunch of dirt in a pile. It's the same material, same color, but different geometry. And it seems like there's different textures to these two dirts. So I just extracted a bunch of patches, clustered them based on their texture, and indeed the dirt on the ground went into one cluster, and the dirt that's in the pile went on into another cluster. So that showed that there's some very basic textural differences that can be a clue to the geometry of this material. So it's kind of a weird idea to think about that you could recognize a geometry, because anything could be around. A certain geometry could really look like anything. You could always, project something onto a surface to make it look however you want. But this led me to think that, well, there's enough structure in real-world environments and the way that people take photos that maybe we can treat geometry estimation as a recognition problem. And so the idea was to create these very simple geometric classes that kind of roughly describe the geometry of the scene. For example, in this image here, the pixels can be described as being part of the sky or some vertical surface or some support or ground surface. And then the vertical surfaces can be further described as non-planar or planar. If they're non-planar, it could be porous, like tree leaves or wiry meshes. Or they could be solid, like people or cars or rocks. And then planar surfaces could have different orientations. So it's a really rough description of the geometry. And then we can treat this geometry estimation problem as one of recognition, because now we can take a bunch of images, label all the pixels into these geometric classes, and then we have training data where we can extract features, so we know we have some description of the regions, and we have a label that we want to predict. And then we can train a classifier that, based on color, texture, perspective, location, and maybe some other features, is able to try to predict which geometric class a particular region belongs to. So for example, here the classifier should say that this is a vertical planar region and it's facing the right. So the algorithm then to try to infer the geometry from the scene, or infer this structure really from the scene, is very simple. Just divides the image into a bunch of different overlapping regions. For each region, predict, is it part of the ground, vertical surface, or the sky, along with those subclasses. And then average those predictions across the regions that contain each pixel to produce a final map. And so in this map, the green pixels are ones where the computer thinks it's part of the ground, the red sky, the blue sky, the red vertical. And so it's just, again, a very rough description. But it kind of works well across a wide variety of scenes. And that was surprising to me. So here's the dirt pile on the bottom. It worked reasonably well for that. It works for city scenes. It even worked on paintings, snowy scenes, and things. It generalized in ways that was a little bit surprising to me. Still, though, at this point, all we have is this. Now we have a 2D map of geometric labels. So it tells us something about the geometry, but there's not really a 3D representation there. So then the next step is to fit a very simple geometric model to this more structural representation of the scene. I would think of it as that this label map is giving us the structure of the geometry, and then we have a simple model that's giving us the actual 3D geometry. In this case, the method is it's kind of similar to creating a pop-up book, where if you want to pop up an object, then you would fold at the bottom of the object, and then cut on the edges of the object, and then you pop it up. So it's the same way here. You create boundaries between the vertical surface and the ground, and cut along the edges of those boundaries, and between the vertical surface and the sky, and that creates a very simple 3D pop-up model. So this is automatically created from a single image. And it's a very simple model, just a few planes, but it can feel compelling because it reflects the structure of the scene. You've got the boundaries on the edges of the objects, and the texture can kind of help fill in the details. Here's a couple more examples. So in this case, there's a little bit more going on. There's also an algorithm that's trying to find more specifically trying to find the edges of objects so that you can separate the foreground objects from the background objects. But it's the same basic idea. The depth is just estimated based on how high in the visual field the object touches the ground. Here's one more example. So you can apply recognition algorithms as well to try to do a better job of finding the boundaries. But I think the key lesson here is that even with very simple geometric models, if your models encode the structure that's in the scene, if it encodes what are complete surfaces and where are the edges of objects and so on, then you can create fairly realistic or representations that feel realistic and create a good experience. So here's another example. So here we've got an indoor scene, and this was work that was done with my student Chuhong Zhao and Qi Shan and Alex Colburn, so work that we did with Zillow. And so here we have a panorama of an indoor scene. And then here's a 3D model that was created from that panorama. And I'll explain how we did it in a moment. So still a very simple representation, but going from one image of the scene to this 3D representation. So all the details of this technique are different than the previous method. We're using deep networks. There's not a completely different feature extraction, no segmentation. But it's the same basic idea of trying to recognize the features of geometry and fit a simple model. In this case, the features of geometry are a map of the boundaries. So what are in that panoramic image, which pixels correspond to the boundaries between the floor and the walls, between the walls and the walls, and between the walls and the ceiling? And then where are the corners? And we've got a deep network that's taking as input the panorama and detected lines, and then just predicting all of these boundaries and corners. And then we fit a really simple model to it. It's either a box model, just like a cube that can have different dimensions, or a L-shaped model. And that the key to many of these approaches is finding the simplest model, the lowest parameter model, that gives you just enough realism for your application, or gives you enough of a sense of the scene geometry. So an example application is augmented reality from one image. So here, there's an image here that we got from the internet. We put a bunch of fake objects in it. Look at it for a moment and see if you can figure out where the fakes are. Some of them will be really easy because they're things you would never find in a kitchen. In fact, most of them are probably things you would never find in a kitchen. But so does anyone want to hazard a guess? Can you point out an easy one? Which one? This thing? The light? That? No, that's real. Yeah, so so somebody said the thing's on the counter. This is fake, and that's fake. The plants are real. Yep, the Buddha. Very few people have that in their kitchen. Yeah, and then that weird, I don't know what it is, a donut or something, I don't know, some weird tube on the floor, yeah. So sometimes people also think the penguin is fake, but that's real too. So here's the original image on the left. There's the scene with the objects put in it on the right. And in this case, this is the magic behind it. This is the model that is used in order to realistically insert those other objects. So we've got a background image. We've got some meshes of these objects, some graphics objects, 3D graphics objects for those other objects. And then we're able to cast shadows and caustics, interactive lighting effects, occlusions. And it's this really simple model where we just have the basic geometry fitting a box to the scene, locations of the lights, some extruded polygon for the counter, and then some matted segment for the occluding objects. And in this paper, in the original paper, which was like 7 years ago, this was a manual markup that took like about a minute. But since then, the first author, Kevin Karsh, went on and did this fully automatically. So now you can fully automatically get this kind of representation and insert objects realistically. So when you can do that, then you can take, here's another picture we download from the internet of a pool table. You can simulate a game of pool on that table. So it feels like everything is interacting with 3D surfaces, even though it's all just derived from a single image. And then here's another example where we put a glowing ball inside of a room. So it's, there's reflections, it's lighting up surfaces, casting shadows, moving behind things, and it all comes from this really simple representation. So you can also do quite a lot from single view reconstruction, but it has its own limitations. So one limitation is limited applicability, that typically recognition methods only work well on the kinds of images that they've been trained on. So if you train a method on indoor images, it's probably not going to work well outdoors. Or if you train a method on forest scenes, it might not work well in a city. And so typically you create special purpose algorithms for specific cases. And not only do you need to have similar images to learn from, but often the ideal models for these different situations would be different. So like the model that we use for outdoor scenes is basically like billboards or little planes that are popped up on the ground, where for indoor scenes it's more boxy structures. And then the other main limitation is that these models are very geometrically simple. There's very few planes to these models, where the 3D model of the construction scene that I showed you has tens of millions of points. It's extremely detailed. These models can be represented in probably a few kilobytes or less. It's like really just, they can be represented with 20 or 30 points, really. They're very basic models. So in single view reconstruction, this is an example of the latest and greatest, or the bleeding edge. So the interesting thing is that there's the ability to predict lots of things, do many different kinds of recognition and regression on images has improved quite a lot, largely due to deep networks. So here the idea is that from a single image, you predict a depth map, and that depth map is pretty terrible, but it still kind of encodes something about the scene structure. You predict a surface normal map. That tends to be a bit better. Still not nearly as good as what you would get from multi-view geometry, but you can see that there's like flat surfaces on the bed and the floor, and it's roughly getting the orientations correct. And then predict an object mask, doing semantic segmentation to label which pixels are lamp or bed or floor. And then the idea is to have some optimization algorithm that's solving for the locations of the wall and floor and the locations of 3D objects in the scene, so that when you render the model, it renders something that's similar to the original image. Not similar in the colors, but similar in that it produces a similar depth map and surface normal map and object mask map. So here, from this image, the authors, and this is Huang et al., not me, were able to get a this 3D model of that scene. And so it's not a perfect representation, but it really does encode the structure of the scene very well. It's recognized the objects, it has their spatial layouts, and knows which objects are sitting on top of which other objects, and so on. So I think that the challenge and opportunity for the future is really, how do we get the best of both worlds? So what we want is the detailed geometry that we can get if we have multiple images, and we want the structure and semantics that we can readily extract from a single image. And the opportunity now is that deep networks can serve as an interface between these two methods. That's really what's valuable about deep networks, is they're an interface between different tasks or different data sets. The representations that are learned on the inner layers can be easily shared across multiple tasks. So for example, if we're doing multi-view stereo using deep networks to learn the matching function for producing the depth maps, then we can combine that, we can integrate that with deep networks where we're trying to predict the semantic segmentation of the scene, or to predict the surface normals and depths from single images. So that way, in places where we have multiple images, we can predict the geometry very robustly and in a lot of detail. And in places where we have less coverage, we can still kind of fill in the gaps by predicting from single images, as well as producing semantics throughout the scene. So this has a lot of promise and will impact many different applications. So in construction, for example, we'll be able to do automated progress monitoring, where the system will be able to automatically say how much of the plan has actually been constructed, and do further analysis on schedule risk, for example, as well as analyzing productivity and automated safety monitoring. So at the same time that it's analyzing the geometry and what's actually been constructed, it can find the person that's not wearing their hard hat but should be, and warn the superintendent about safety issues, or find that there's a ledge where there should be a fence but there's not. Another key application, is in augmented reality. So right now, even though it's kind of technically impressive, the augmented reality that I've seen out there anyway from Magic Leap and so on is basically like an Atari level of complexity. It tends to be very simple modes of interaction and very simple interfaces, because you really need to understand a lot about the geometry and semantics of a scene to put characters and put objects in it that are interacting with that scene. So if we can wed together the multi-view and single-view techniques, then we can get that structure and semantics and detailed geometry that we need to create really realistic virtual interactions. And then the third one is that robots will finally be able to see. So if you're interacting with objects, then you need to know all kinds of things about your environment: the weight, the smoothness, the shape of the surfaces, and to also, of course, understand the semantics so that you can perform meaningful tasks. And so these are just a few of the really amazing applications that I think will be enabled as we're able to wed together the semantic understanding that we can get currently from recognition algorithms with the geometric understanding that can be produced from multi-view stereo. So thank you very much for your attention. Now I'm happy to take questions. Sure. So for the future one, I can't go to too many details because I haven't thought of them yet. But the layout net, I'll try to do that. Okay, so for layout net, basically the idea is to create a very simple approximation of the layout of the surfaces. So you might see very faintly here these lines. So these are the boundaries of the walls with the floor, and these are corners. So in some complex scenes, the model may be too simple to capture the full geometry of that scene. In this room, for example, there's lots of angled walls and stuff, so it would only be a coarse approximation. But the basic, what the algorithm does is tries to predict these boundaries in general. So whether or not it's a simple shape or not, try to find all the boundaries between the walls and floors and ceiling, as well as the corners between those boundaries. And that produces these boundary maps. So the green line is showing the ceiling wall boundary, the red is wall boundary, and the blue is floor wall boundary. And if I forgot to repeat the question, sorry, it was to ask about more details of some of these models, for example, layout net. So the deep network predicts these confidence maps for the boundaries and the corners. And then we have, and then the one part, what's not part of the deep network is an optimization algorithm that, given these boundary maps, tries to solve for the 3D structure that best projects onto these boundaries. So the 3D layout, which in the simplest case would just be some oriented box, such that the corners of the box project onto these corners, and the boundaries of the box project onto these boundaries. Yeah, and the Manhattan lines is from a separate process. So one of the things that, one of the kind of ideas of the research is that there are some parts to the geometry estimation process that are not best approached through black box recognition. So we're using like a deep network to predict these boundary maps and corner maps, but we don't really need we don't want or need a deep network to try to extract these lines or cluster them into different orientations. And likewise, once we have this boundary map, we can use a deep network to try to regress the final 3D scene parameters, but it doesn't work as well as if we do a simple optimization. So sometimes, especially if you're dealing with very structured predictions or geometry, you need to kind of figure out how do you combine the pattern matching with your knowledge of the geometric process or the camera formation process.
I have a question. So for the data set that you used, you mentioned that if the image or if the scene is not similar to one that it was exposed before, then it won't perform as well. So how many images you had to annotate, and was that a manual process to annotate those images? And like for the future usage, do you have always to annotate scenes that never seen before, or yeah, it's all about the data set. Like, was it manually created? How big is the data set in order to get good results?
So the first method I showed for automatic photo pop-up and those first like fly-throughs with the rocks and so on, there were only 250 training images. And I did annotate them by hand myself. It took like 40 hours or something, because all the pixels were labeled. So it took a long time personally. But now data sets tend to be much bigger, tens of thousands or hundreds of thousands of images. And one common way that this is, one common thing now in single view reconstruction for current methods is that they'll use synthetic data, at least to bootstrap the process. So you can render like pretty good realistic models of 3D scenes and render, there's one recent data set for interiors where there's 20 million images that are rendered, or 20 million scenes. So you can create a lot of synthetic data, and then often you want to combine that with a little bit of maybe a few thousand or a few hundred at least actual like natural images, so that you're making sure that you're not overfitting the synthetic data.
Hi. Here. My takeaway from this was, with Photoshop, we could not trust pictures. Now we can't trust videos either.
That's what the journalists always say.
Yes, exactly. But I had a different question. Being from academia, what do you think we can do to collaborate better between academia and industry to realize the future sooner? I just want to hear your thoughts.
Yeah, that's a good question. So how does academia better collaborate with industry? I think the main thing is that it's good for academics to every now and then do something different. So to just go outside of the normal process of writing papers and grant proposals and doing basic research, and just go try something that interacts with the rest of the world. So in my case, it was Reconstruct, like co-founding Reconstruct and trying to figure out how we can impact the construction industry. But it could be just going and doing a sabbatical at Zillow or at another company. I think that there's many good ways to interact with industry, and it's extremely easy now. I think universities are generally pretty open to different forms of collaboration, and many companies are really eager to collaborate with faculty or students. So I think it's just a matter of like pushing yourself to do something that might be a little bit uncomfortable.
I'll just shut it up. So the practical side of it, our company would like to have real quick, cheap ways of getting maps and plans of insides of buildings, commercial buildings. So how can you bring both the process of taking the pictures down, I love taking one panorama and that's it, right? And have the cost be very, very low for us because we have to charge real low. We work with small and medium-sized buildings, energy efficiency, and we can't charge a lot for this. And it's not for prettiness, it's for real practical applications.
Right. Yeah, that's a very big problem. I mean, we at Reconstruct, we're also very interested in ways to capture the geometry of indoor scenes and to do it cheaply and quickly. I don't have an awesome answer to the to the question though, but I think at least like the use of, I think the direction is basically the use of video or use of video with 360 cameras. So that, especially with 360 cameras, then you get the completeness. And the video is just much faster than if you have to go from, take photos at many different locations. Then if you want to, there's always like a big trade-off between the technical complexity and the capture complexity. If you're willing to do a lot on the capture complexity, then your technical problem becomes very simple. But if you are not, let's say you say, okay, now I want somebody just to use an iPhone and like take panoramas like this, which creates like sort of fake panoramas because they're not all from the same position, and then go around in a few spots and do that. Then the technical problem becomes a lot harder, and that's really like, that's a more than 1 year research problem, yeah. And yeah, it's expensive if you're gonna try to develop that solution.
Where? Great job.
Thanks.